So let's solve another problem. Here we have the cross correlation expression that is given to us. Remember, we have seen this earlier when we were talking about signals and solving some problems there. Now this looks very similar to the convolution expression, but it is not the same, because convolution of x of t with y of t is nothing but minus infinity to infinity x of t minus v y of v dv. This is the convolution expression. But if you have a plus here, then you get the correlation expression. So they are different. They look similar, but they are different. We know that convolution is commutative, which means that this is same as y of t convolved with x of t. But we also saw earlier that correlation is not commutative, meaning Rxy of t is not equal to Ryx of t. Okay. So why is that? Because we can say that, let us say t plus v is equal to some s, then we have integral x of s times y of minus t plus s times ds is equal to Rxy of t. But this expression is basically nothing but Ryx of minus t. Okay. So clearly Ryx is not the same as Rxy. So this says that the cross correlation is not commutative. But when will it be commutative? If it is commutative, then we know that Rxy of t should be equal to Ryx of t. So it becomes commutative when Ryx of minus t is equal to Ryx of t. In other words, Rxy of t is equal to Rxy of minus t. In other words, if the cross correlation is an even signal, whenever they are even, they become commutative. You can find this integral in any order and you will still get the same output. So cross correlation becomes a commutative operation when the cross correlation signal is an even signal. So we saw that the convolution and the cross correlation have different expressions and they are not exactly the same. So is it possible for certain signals that they may end up giving the same result as in? Is it possible under certain conditions that cross correlation is the same as convolution? So under cross correlation, we have x of t plus v multiplied with y of v and then integrated, whereas here we have x of t minus v and multiplied that with y of t and then integrated out over t. Now what if we consider the output for negative values of time? So let us say t is negative, which means you can say x of minus t. X of minus t is now positive. So x of minus t minus v times y of t. Okay. So now this is x of t plus v times y of v. Now let us say that the signal x of t is even. If the signal x of t is even, then we have x of minus t plus v to be exactly the same as x of t plus v. Okay. So this becomes x of t plus v times y of v. So we started out with the convolution. We said that some z of t is equal to this convolution operation, and then we considered z of minus t, and we said the z of minus t is nothing but x of minus t minus v y of t dv. Okay, and all we did was we assumed that for x of t that is even, we get that z of minus t is this expression, which is nothing but the cross correlation between Rxy of t. So we can say that the cross correlation when you have an even signal is equal to the time reversed version of its convolution. So this is the time reversed version of the convolution. Okay. Or in other words, can say that x of t star y of t is rxy of minus t, which is in fact equal to ryx of t. This is true only for even signals. Okay. So, when you have even signals, you can find a relationship between the convolution and the cross correlation, otherwise it is not really possible. In many practical audio systems, we have this problem of echo, right. So, what is echo? It means that there is an audio signal which gets reflected off some surface, and at the receiver, which is let's say a microphone or some listener, you get not only the original signal but also this reflected signal. So, if there is a speaker somewhere in a room, let's say there is a room and there is a speaker, and let's say there is a microphone here. So, the direct signal comes to the microphone, but it is also possible that it gets reflected off a surface and then also is received at the. Now, the direct signal travels only a shorter distance and hence it comes faster compared to the reflected signal. The reflected signal takes a longer time because it travels a larger distance and then appears at the receiver, which means if the signal x of t is played as the audio here, what would you receive here? The signal received at the microphone is not just x of t, but also a time delayed version of the signal. So, you will get the x of t that is related to this path, which is the shortest path, but there is also a delayed version because of the long travel, and that is x of t minus t. This is what we call as the echo. So, this is what we receive. So, when there are multiple reflectors, we will have more echoes. So, here we assume there is only one reflector and we receive one echo. Okay. Now, if this is a system that is given to us, so is this an LTA system? Yes, it is an LTA system. We can check that. Let's say we have inputs x1 of t and x2 of t. Then what would be the output? The corresponding output would have been a times x1 of t plus b x2 of t produced as such, plus their time delayed versions. Okay. But remember, this exactly is nothing but a times y1 of t, and this is exactly nothing but b times y2 of t. So, this satisfies the linearity equation. So, hence this is a linear system. Is it time invariant? Yes, it is time invariant. As you can see that if you feed in an input x of t minus some t naught, then the corresponding output would be x of t minus t naught plus x of t minus t naught, which is equal to y of t minus t naught. So, this is an LTA system. Turns out to be an LTA system, so we can easily model that using an LTA system. So, which is good for us because we know how to model and understand LTA systems. What do we need? We need the impulse response. So, what is the impulse response of this LTA system? It is quite straightforward. What is that? That there is an h of t, when you convolve that with the input, you get the input itself plus a delayed version of the input. So, what is the signal with which when you convolve some x of t, you get x of t itself? That would be the Dirac delta signal. So, h of t is the Dirac delta for the first term. And what about the second term? It is once again Dirac delta shifted by this time. This is once again the property of Dirac delta signal. So, any room where you have echoes, you can model the input-output relationship between the audio in that room using a sum of Dirac delta functions, which looks like this. So, the impulse response of this echo creation or this room which creates echo is given by this sum of Dirac deltas. When there are two echoes, you have just two Dirac deltas. When there are multiple, you have multiple Dirac deltas. So, this is the impulse response of this echo creator system. So, the echo creator system, it is LTI. It has an impulse response which is given by Dirac delta, and we know that the area of the Dirac delta function is just 1, which means this system is actually stable. okay, and it is also causal. So we know the properties now. Now let us say at the microphone you want to cancel these echoes. Then what do you do? So let us say you construct a system which looks like this. So you take the received signal and then you construct a system which looks like this, where the output of the system is delayed by some t, and then that is fed back to the input, and then it is subtracted off. So if this is the case, then what exactly happens here? So the output is now some z of t. So the delay introduced here is z of t minus some t, and that is added back here. So what you get here is y of t minus z of t minus some t. So this makes sense because what we know is that the echo comes only with a delay of t. So the first t seconds, capital T seconds, does not have any echo. So you pass the first capital T seconds as such, then copy whatever that was present in the first capital T seconds, that is this delay element, and then subtract it out with whatever signal that you receive after the capital T seconds. So that is what is happening here. Okay. So you can keep doing this repeatedly, because once you subtract this out, the signal that you get out of here will now not have any echoes. So the next t seconds will not have any echoes. You delay that, once again subtract it out from the next capital T seconds, and this keeps repeating, right. So what we have here is another system which will cancel out these echoes. So intuitively we can say that this is an echo canceller. So how does this input output system look like? So you have z of t equal to y of t minus z of t minus t. Okay. So this is the input output relationship of the system that we have here. So once again, this is an LTA system. So if we want to find the impulse response of this system, how would it look like? Then for an impulse del of t, the output is given by z of t plus z of t minus t. So this is the output that we get for an impulse where y of t is the impulse. Okay. So what would be the impulse response that would satisfy this equation? In other words, what we are saying is there is a h of t, something like this. When you delay that h of t by t seconds and then add them together, this summation gives a Dirac delta. So what could possibly be such a h of t? So clearly what this says is you are delaying that by capital T. So from 0 to capital T, there is only one component that is present, and that is equal to the Dirac delta, because the Dirac delta is at 0. So the h of t, if you want to plot, what does it contain? It contains a Dirac delta at t is equal to 0. Only then when you delay it, you are delaying it by t seconds. So when you delay it by t seconds, the Dirac delta now is at t. Now we have to construct an signal h of t such that when you delay the signal h of t, so let us say there is a signal which looks, it's a causal system. So for negative values of time will be nothing. Let us say there is a system something like this, okay, and you delay it by some capital T, and you add them up. When you add them up, what do you get? You will simply get a Dirac delta. So clearly when you add them up, there is nothing in the delayed version in this time duration capital T. And when you add, you get a Dirac delta, which means there needs to be a Dirac delta here. So it means that the h of t has a Dirac delta at t is equal to 0, and there is nothing for the next capital T seconds. So in this portion it is empty. Okay, only then you can get this part. Okay, what happens after that? So after that, still you are supposed to get 0, which means whatever is present here is equal to whatever is present here. So what is present here? We already know that there is a Dirac delta here. So which means there has to be a negative Dirac delta at this point. So which means we have a negative Dirac delta here. alright. So, which tells us that there is a negative Dirac delta, which means there is a negative Dirac delta here after capital T seconds. There is nothing here because it is simply a shifted version. So, we have a negative Dirac delta here, which when added up with the original signal has to once again give 0 here, which means there is a positive Dirac delta here, okay, which tells us that after capital T seconds there is a positive Dirac delta here. Now, if there is a positive Dirac delta, there is the shifted version also, there is a positive Dirac delta, which also has to get cancelled out. So, this keeps repeating alternatively. So, there is a negative Dirac delta for every capital 2t seconds, and there is a positive Dirac delta for every capital 2t seconds, and it keeps infinitely going on. So, this is the impulse response of the echo canceller. So, this is the impulse response of the echo canceller, which will cancel the echo, and this is the impulse response of the echo creator. Clearly, the echo creator is stable, but as you have infinitely many impulses in the impulse response of the echo canceller, each of this has area 1 and the total area will become infinity, which means the echo canceller is actually unstable. The echo creator is stable, but the echo canceller actually can end up being unstable. So, you need to carefully operate the system when you cancel echoes.